In this video, we're going to be talking about linear approximations and differentials. This is a relatively straightforward section, but there is a little bit of tricky definitions later on where we talk about the difference between the function values and the difference between the linear approximation, which is on the tangent line. When we get to that section, we'll be using the graph in order to make it more clear what we're talking about when we talk about the difference in the y values on the function compared to the difference in the y values on the linear approximation, which is the tangent line. To start with, though, we want to realize that we sometimes want to use linear functions to approximate functions that are by definition not linear. Now, we can only do this if these functions happen to be differentiable. In other words, if we zoom in on the function and it stays something that looks more and more linear as we continue to zoom in, then we can approximate the function using a linear function over a short, small interval. This idea is going to be used again later in this course and in following courses where we'll use an approximation to a function to find the value of a function that might be rather difficult to find. In the first definition that we have here, we want the linear approximation of a function at a point. So we want to think about a function that's differentiable. That means automatically that the function is continuous because it has a derivative and it doesn't have a pointed part like a corner or a cusp, or it wouldn't be differentiable. Now the function needs to be differentiable at the point x equal a. Recall that the equation for the tangent line to the graph of the function at a is given by the equation y equals f of a plus f prime of a times x minus a. Now, this is really just the point slope form of the equation in disguise, where we have y minus y1 equal to the slope of the tangent line times x minus x1. Remember that the slope of the tangent line is the derivative at that point. This implies, of course, that the derivative does exist at a since we're using f prime of a. This is the equation of the tangent line to the graph of f at the point a. If the function is differentiable at that location, the tangent line will be close to the function at that point. Let's take a look at this graph right here on the left. This is the graph, or half of the graph, of the rational function 1 over x that you see in this orange-red color here. When you're looking at the function, notice that they have drawn the tangent line at the point x equal 2. The tangent line is the straight dark blue line that you see here. As long as you're very close to 2, the graph of the tangent line that you see in the right graph is very close to the graph of the actual function, which you see here in the red-orange color. So long as you are close to 2, it is true that the tangent line graph is very close to the graph of the function. Now, if you got further away, say down here at 1/2, then it's not at all close to the function. The tangent line is down here and the function's up here. But as long as you stay close to 2, where you graph the tangent line, then the graph of the tangent line is close to the graph of the function. And that means that we can use the tangent line to approximate the function, given that the function 1 over x is more difficult to deal with since it's a rational function. We can then say that the function value there is approximately equal to the equation of the tangent line. So this is the actual function value that you see here on the left, actual function value f of x, which is approximately equal to the value on the tangent line. In other words, the one on the left is that red-orange graph, and the one on the right is that dark blue graph. As long as we stay close to the value of a, they should be a decent approximation. We call this expression that you see on the right side the linear approximation or tangent line approximation for the function f at the point x equal a. It's really just the equation of the tangent line. It's also called the linearization of f at a, because what you're doing is you're taking a curved graph and you're using instead the tangent line graph, which of course is straight. And as long as you stay really close to that point A, it'll be a good approximation. Now, really close is kind of arbitrary, but you can see that in that region right there, the tangent line does stay close to the graph. Linear approximations are really useful for approximating roots and powers, and also for trig functions. You can also use them for e to the x and natural log of x. They're really good for approximating things that are not easily calculated by hand. In fact, it gives you a way of calculating it by hand. Let's take a look at our first example. In the first example, we want to find the local linear approximation, in other words, the tangent line, to the function f of x equals the cube root of x at x equals 8. We want to use it to approximate the cube root of 8.1 to 5 decimal places. Okay, 5 decimal places, that's a lot. And we're doing this by hand. Okay, what does that mean? First, we need the linear approximation function, which you see here. To do the linear approximation function, I need the original function f evaluated at x equal to a. Our value of a is 8. So if we evaluate the original function f of x equal to the cube root of x at 8, then this gives me the cube root of 8, which I know to be 2. I also need the derivative of the function. So I come back to the original function, f of x, and I rewrite it in its power notation form as x to the rational power 1/3. Then I can take the derivative of that, and this will give me 1/3 x to the negative 2/3. Remember, the negative sends it to the denominator. So this gives me 1/3 x to the 2/3 power. I can also think about this as the cube root of x squared if I want to think of it that way. That's another good way of writing the fractional exponents. 1/3, the cube root of x squared. When I'm looking at this then, this is the expression for f prime. I need f prime at a. In other words, I need this at 8. So I need f prime of 8. I then plug the 8 into the value for the function, and I get the cube root of 8 quantity squared. Well, I know what the cube root of 8 is. The cube root of 8, of course, is 2, and 2 squared would give me 4. This gives me 1/3 times 4, which is 1/12. You could also have done it in the other order, where you do 1/3 times the cube root of 8 squared, which would give you 64. The cube root of 64 is 4, and you still end up with 1/12. However, it's easier to make it smaller first and then to make it larger. So we typically do the cube root first and then raise it to the power. What's the next thing that we want to do? We need to plug these pieces of the linear approximation function into the formula to find the formula. The linear approximation function, otherwise known as the tangent line at 8, is then going to be given by the following function. This is going to be f of a, which we have already computed to be 2, plus f prime of a, which we have computed to be 1/12, times x minus a, which is 8. This is the linear approximation function. You can leave it in this form, it's just fine. Now we want to use that to approximate the cube root of 8.21 to 5 decimal places. I certainly have no idea, really, what the cube root of 8.1 is, although I'm guessing it's fairly close to 2. But I want this to be the 5 decimal places, and I'm approximating. How do I approximate? I want to find the cube root of 8.1, so I take 8.1 and plug it into the linear approximation function. This gives me 8.1 equal to 2 plus 112 times 8.1 minus 8. 8.1 minus 8 is the same as 110, which gives me 2 plus 112 times 110. 112 times 1/10 is 1 over 120. This gives me 2 plus 1 over 120. The next thing you need to do is grab your calculator to see what that fraction becomes. But basically what you've done is you've approximated a cube root without ever doing the cube root itself on the calculator. 2 plus 1 over 120 comes out to be approximately, let me see, 2.08333, repeating. Now that I have that, I'm wondering what the real value of this is. If I want to know, I can take 8.1 and take the cube root of it, or in other words, raise it to the 1/3 power. When I do the cube root of 8.1 and the calculator, I get 2.008298885, which is, in fact, remarkably close to what I got down here. It's only in the 4th decimal place that they differ, and not by much. This is a very easy way of getting approximations to some of the ones that you might not be able to compute by hand if you don't have a calculator handy. Yes, you could divide 1 by 120 by hand if you had to. Let's now take a look at example 2 and see what example 2 looks like. In example 2, we're to find the linear approximation function for f of x equal to the cosine of x at x equal to pi over 2. Again, we need to find the pieces of the linear approximation function, the function value at a and the derivative at a. Our value of a right here is going to be pi over 2. For the function value at a, I have the function value at pi over 2, which is basically the cosine of pi over 2, which I know to be 0. Now I can find f prime of x using the original function cosine of x, and that gives me negative sine of x. Then I plug in the value of a, and I get f prime at a equal to f prime of pi over 2, which is a negative times the sine of pi over 2. Sine of pi over 2 is 1, so this gives me a negative 1. Plugging these pieces into the linear approximation function leads to the following expression. I get L of x equal to 0 minus 1 times x minus pi over 2. Since pi over 2 was the value of a. In other words, I can approximate the cosine close to pi over 2 with the linear equation negative 1 times x minus pi over 2 or negative x plus pi over 2. If I were to take something relatively close to pi over 2, say 80 degrees in radian form, or 100 degrees in radian form, I would get an approximation for the cosine value at that particular angle. Let's now take a look at example 3. In example 3, we want to find the linear approximation of f of x equal to 1 plus x quantity to the 4th at x equals 0, and use it to approximate the value of 1.01 to the 4th power. When we're doing this, what we can do then is find the value of a, which is 0 in this equation. Then we can find the value of f of a from the linear approximation function as f of 0, which is equal to 1 plus 0 raised to the 4, which is 1 to the 4th, which is 1. Then we find the derivative f prime of x, and we use it to find f prime of a, which is f prime of 1, or 0 rather. Now we have f prime of x. We apply the chain rule up here, and this gives us 4 times 1 plus x to the 3rd power times the derivative of the inside function, which is 1. This gives us 4 times the quantity 1 plus x raised to the 3rd. When I plug in the value of a, which is 0, I get 4 times 1 plus 0 raised to the 3rd, which is 4 times 1 raised to the 3rd, or just 4. Now I can put this into the linear approximation function, which is really just the tangent line at the point 0. This gives me f of a is 1 plus the derivative at that point, which is 4 times x minus 0. I can simplify this equation and write it as 1 plus 4x. You may, on the other hand, want to leave it in the other form if you prefer. Now what we want to find is L of 1.01. In order to find L of 1.01, I need to figure out how far away I am. In this case, what is the value of x? I started with x out there at 0, and now I have 1.01. The problem that I'm encountering now is that I don't actually want L of 1.01. That's not all that close to 0. What I really want to know is what's the value of 1.01 to the 4. But I need to rewrite this 1.01 to the 4th power in the same format as my original function, which was 1 plus something to the 4th power. I can then write the 1.01 as 1 plus 0.01 raised to the 4th. In other words, the value of x here is 0.1. So what I want to find is not L of 1.01, but L of 0.01. 0.01 or 0.1 is close to 0. So now I'm finding L of 0.1 by plugging that into my expression for the linear approximation function, or the tangent line, which gives me 1 plus 4 times 0.1, which is basically going to give me 1.4. When I take 1.01 and I raise it to the 4th power using a calculator, did I do that right, or did I mess up my number? Oops, I did mess up my number. This is supposed to be a 0, 1, so that would be a 0, 1. So this would be a 0.04, 1.04. When I take 1.01 and I raise it to the 4th power, what do you get? I get about 1.04060401. So the true value, or as true as it gets from the calculator, is approximately 1.04060401. And my approximation is really quite close. I like to use the linear approximation function when I'm doing something and I need to calculate square roots. That would probably be the time I use it the most. Then sometimes you don't always know what the value of A is. Let's take a look at an example that I'll make up here on the spur of the moment. Okay, let's suppose that you were given another example, and we'll call this example 3B. And you were asked to find, the square root of 118 by hand. All right, well, this is not something I typically know. I don't know what the square root of 118 is, and I'm not given an a value, but I can approximate this using the linear approximation function by realizing that 118 is close to 121. And the square root of 121 is 11. In other words, I can set my a to be equal to 121. And I can set my function to be equal to the square root of x. Then f of a becomes the square root of 121, which is 11. Then I can compute the derivative of the function, which of course will give me 1 over 2, the square root of x. Then I can find that value at a, which is going to be 1 over 2, the square root of 121, which is 1 over 2 times 11, or 1/22. Now I can plug the pieces into the linear approximation function, and I'll be able to approximate the square root of 118 by hand, or with fractions only, without needing the calculator to do the square root. What does this give me? It gives me L of x, the linear approximation function, which is just the tangent line, f of a, which is 11, plus f prime of a, which is 1 over 22 times x minus a. Now I want to use this to approximate the square root of 118. So I plug in 118 in place of my function. Oops, somehow I got a 12 instead of a 22. This gives me 118 minus my a value. And remember, my a value was 121. Don't be worried about the fact that 118 minus 121 is negative. All that means is that I'm going to be subtracting something from 11 because it should be slightly smaller than 11, which should make sense to you. 118 minus 121 gives me 3. This tells me that this becomes 11 minus 3 over 22. If I work this out on a calculator or I do it by hand, I can find that the value of 11 minus 3 divided by 22 is equal to 10 and 19/22, which is about 10.8636, and then it repeats from there. Now the question is, what is the real square root of 118, or at least as close as the calculator can get? The square root of 118, according to the calculator, is about 10.86278. You can see that if you round it up to the third decimal place, they would be the same. They are the same out to the second decimal place. This gives me a very accurate way of computing by hand what a square root is, and all I need to know is a square root close by. Could I have used the square root of 100? Yes, but it's further away, so it won't be as accurate. The closer the square root value is to your value, the better the approximation will be. Now we want to take a look at something called differentials, and we want to define what the differential actually is. This is the first time this semester that we've actually defined a differential, although we've been using differentials since we learned derivatives. The linear approximation function can be used to estimate a function value and how much it changes as a result of a small change in the input. The differentials are dx and dy. That's what we call a differential. Notice that we've been using them in the derivative notation dy dx. Again, these represent a way of measuring how much one function changes as a result of a small change in input values. What is the connection between the differential and the linear approximation function? Remember that we started with a function that's differentiable at a point. We are going to let the x input change by a small amount, and we're interested in how much the output y changes. So we let x change from a to a plus dx, or you can call it a plus delta x, either one, where this delta x is a small amount of change. And the amount of change is that delta x or dx, and the change in y is given by delta y is equal to the function of a plus dx minus f of a. Really and truthfully, these should be delta x's because we're talking about the true function value and the difference between a and delta x and f of a. It just turns out that dx and delta x are the same. Delta x is on the original function, and it's the change in the x value. Dx is on the linear approximation function, or on the graph of the tangent line. It just turns out that dx and delta x are always the same amount. dy and delta y, however, are not. They are not the same amount. They're slightly different. Instead of calculating the exact change, delta y, we can approximate it using the linear approximation function, which is the tangent line. We want to take a look at what happens when we calculate this on the tangent line. Let's suppose that we take this a plus delta x and we subtract L of a. We're going to use the definition of L of x equal to f of a plus f prime of a times x minus a. Remember, this is just point slope form of the line, where you've moved the y1 to the other side. This is slope of the tangent line, and this is x minus x1. It really is the tangent line. When we use the definition for L of a plus delta x, we still have f of a plus f prime of a times a plus delta x minus a. Notice that all that gets replaced when we replace the a plus delta x with x here becomes just this part in the expression. Notice this gives us an a minus a, which just becomes delta x. When we substitute a, we get f of a, the constant, f prime of a, which is also a constant, and we substitute a in place of the x to get a minus a. But a minus a goes to 0. And since we have that, we end up with minus f of a coming from here. But then we have f of a minus f of a. So we end up with the change on the linear approximation function being f prime of a delta x. In other words, if we change by the same amount of change in the x function, the change we have in the y value on the tangent line is f prime of a delta x. Let's write that over here. Delta L is equal to f prime of a delta x. All right. Now let's look at the picture so that we can understand what the difference between dy and delta y is and why dx and delta x are the same. dx is the change on the tangent line. Notice it goes from this point here on the tangent line that I've outlined now in blue to this point here, also on the tangent line, also now in blue. This is dx. This is the change in x on the linear approximation function, the tangent line. Change in x on tangent line. What is delta x? Well, delta x is the change in x on the actual function. but they're the same. Change in x on f of x, which is this curved dark blue line here. But they're exactly the same. Because one is directly above the other, my delta x on the original function is equal to dx on the approximation function, which is the tangent line. What about the change in the y values? Are those the same? No, they're not. dy is again going to be the change in y on the tangent line. Change in y on the tangent line. That's what dy is. This is the change in y on the tangent line. What about delta y? Delta y is something different. Delta y comes from the black dot down to the lower blue dot. This is delta y. Delta y is the change in y on the function. Notice that there is a slight difference between the delta y and the dy. That difference is this part right here that I'm going to color yellow. That's this difference right here. It's not showing up too well. So let me try and make it a brighter yellow. This distance right here, where you have that from there to there, this is the difference between dy and delta y. They're a little off from each other. The smaller dx is, the smaller the difference between dy and delta y will be, but there will still be a difference. As dx and delta x, which are the same, go to 0, the difference between dy and delta y also goes to 0. Then we can use this approximation to approximate the value on the actual function, f of a plus delta x. If we're looking on the true function, which is a, and again, this could be written with delta x or dx since they're identical, we can approximate it with the value that's on the tangent line, a plus dx. But the value of the equation on the tangent line is equal to f of a constant, plus f prime of a constant, times, replace the x rather, with a plus dx, and then subtract a, which is a constant. The a cancels, and we end up with f of a plus f prime of a times dx. So our approximation then becomes f of a plus f prime of a dx for the change in the true function value. When we subtract the original function value from the value at a, we can subtract the f of a from the linear approximation function, and we get f prime of a dx. This part that you see on the left-hand side is delta y, the true change in the y value on the original function. What you see on the right-hand side of the equation, however, is slightly different. What you see here is the change in the y value on the approximation function. This is approximately equal to dy, which is the change in y on the tangent line. They become equal to each other as delta x and dx go to 0, then the two changes become the same. This means that we can use the differential dy equal to f prime of x dx to approximate the change in y, delta y, if x increases from x equal a to x equal a plus dx. Let's take a look at example 4 and see how to apply this new idea. Looking at example 4, what we have is y equal to x squared plus 2x. We want to find delta y and dy at x equal 3 if dx is 0.2. In order to do this, what is delta y? Delta y is the true change in the y value on the function f of x equals x squared plus 2x. In other words, well, if I'm changing x by 0.2, then I need to figure out what f of 3.02 minus f of 3 really is. This is the true change in the value of the function when x changes from 3 to 3.02. The delta x is dx, which is 0.2. This means I need to plug in 3.02 into my function, which would give me 3.02 quantity squared plus 2 times 3.02. Then I'm going to subtract from that what I get when I plug in 3. So first I plug in 3 squared plus 2 times 3, and I want to subtract that value. What I need to do now is go ahead and compute the two different values. If I take 3.02 and I square it, I come up with, looking at my calculator now, 9.1204. I have 9.1204 plus 2 times 3.02 would be 6.04. I know that 3 squared gives me 9, and 9 plus 6 would give me 15. So I have minus 15. Take your 9.1204, add 6.04, and subtract 15. The real difference that you have in the y value is 0.1604. That's the true change in the y value on the function. Now, how could we approximate this? By using the approximation function. Again, we can approximate using the change on the tangent line, dy equal to f prime at a dx. Let's write that down so we don't forget it. Dy equals f prime of a times dx, where the dy is the change on the tangent line in the y value. My a value here is going to be 3 because my dx was 0.2 and it scooched over to 3.02. I need to find f prime at 3. I come back to my function, which was x squared plus 2x, and I compute the derivative of f. That gives me 2x plus 2. Then I compute f prime of 3, which is 2 times 3 plus 2. 2 times 3 plus 2 gives me 6 plus 2, which gives me 8. Now I take that value and I approximate the change in y value on the real function with the change in the y value on the tangent line instead. That gives me f prime at 3, which is 8, times the dx value, which was 0.2. When I multiply 8 by 0.2, I end up with 1.6. Wait, my bad. Did I do that right? Oh, I think I messed up here. 0.1604. Did I do everything correctly? I think I did. 8 times 0.2, however, gives me 1.6, and I'm a decimal point off. Somewhere I've lost a decimal place. Let's see if we can find it. Well, you'll be happy to know I found the missing decimal place, but it was way back at the beginning. My problem was when I saw this dx, I thought it was 0.02, but it's 0.2. So I should have been computing 3.2 minus f of 3. So this should give me all of these values being slightly different. In other words, I had it off from the very beginning, which probably you knew and were waiting for me to figure out. Now I've got 3.2 quantity squared, which gives me 10.24. That will be better. 10.24, and 2 times 3.2 will give me 6.4. So when I add 6.4 and subtract the 15, which doesn't change, I end up with 1.64. Much better. And now you can see that the change in y value on the real function is quite close to the change in the y value on the tangent line, as long as we stay close to the a value. Our a value is 3, and moving away to 3.2 with a delta x of 0.2 is not far away. Let's now look at calculating the amount of error that we have. Error comes from multiple places. One of the places that error comes from is just from measuring what your delta x is. This is what we call a measurement error. The problem with a measurement error in the value of dx or delta x is that we won't be able to know what the error in the measured value is. We never know exactly what the value of the measurement error is. So it propagates through the entire problem and causes the answer to be slightly off. We can approximate it, though, if f is a differentiable function with the value of the change in the y value on the function being the change in the y value on the tangent line. Since we don't know exactly the value of a, though, we use the measured value of a plus dx instead. That means that the measurement error and the propagated error, delta y, are absolute errors. We're typically interested in the size of the error relative to the size of the quantity being measured or calculated. If you have an absolute error, delta q, for some quantity, we define the relative error as delta q divided by q, where q is the actual value of the quantity. Then turning that number into a percentage becomes the percentage error. Let's take a look at how we can apply this to example 5 of an astronaut using a camera to measure the radius of Earth as 4,000 miles with an error of plus or minus 80 miles. In other words, from using the camera, they know that the Earth is within 80 miles of 4,000 miles, meaning it could be 3,920 miles, or it could be 4,080 miles, or anywhere in between. We'll use differentials to estimate the relative and percentage error of using this radius measurement to calculate the volume of Earth, assuming that the planet is a perfect sphere, which of course it's not. How do we get started? Well, first off, what is the change in the error? What is our error? Our error is plus or minus 80 miles. So the change in the radius, delta radius, or dr, is equal to somewhere between negative 80 miles and positive 80 miles. Either I've got 80 miles too much or 80 miles too few. So we can write that dr is between -80 and 80. Now the volume of a sphere is given by 4/3 pi r cubed. And then we can use implicit differentiation to write dv equals 4 pi r squared dr. Let's review how to do implicit differentiation again. Remember that we want to take the derivative with respect to r of the left side of the equation and the derivative with respect to r of the right side of the equation, 4/3 pi r cubed. Since v is not r, we have to leave it written as dv dr. On the right side, however, this is r cubed, and since we're taking the derivative with respect to r, the differential will disappear. We get the 3 brought to the front, multiplied by the 4/3 pi, and reduce the power on r to r squared. The 3's cancel, and we end up with dv dr equal to 4 pi r squared. Then we do what's called an abuse of notation, where we swing the denominator differential around to the right-hand side. This is an abuse of notation since the derivative operation is an operation and not a fraction, but it works, therefore we do it. Just consider it to be part of the genius of Leibniz's notation. Now we can take the change in the volume, which is dv, and we can express the change in that using the formula on the other side, which is 4 pi r squared dr. That's this equation here now in the box. This is going to be on the left between -4 pi r squared dr less than equal to dv less than equal to 4 pi r squared dr. When we're looking at this, we want to evaluate now the relative error, which is the change in volume divided by the volume. However, we don't know the exact value of the volume because we don't know exactly what the radius is. We use the measured radius of 4,000 miles to estimate the volume. We will have some propagated error, but there's no other way to compute these values. When we use the value of 4,000, we get approximately 4/3 pi times 4,000 cubed. Then we divide the equation by the volume expression. So we take this equation up here and we divide all 3 parts by 4/3 pi 4,000 cubed. What does that give us? Let's write that down below. What we want to do is take this equation that we had up here and rewrite it down here, and then divide each individual part of it by this expression that we got for the approximation of the volume. In other words, divide by 4/3 pi times 4,000 cubed. Divide this by that volume and divide this by 4/3 pi times 4,000 cubed. When you work out the arithmetic, you will find that you have dv divided by v between -0.06 and 0.06. If you convert these to decimals, it's between a -6% and a +6%. The relative error is the decimal number 0.06, and the percentage error is the percent number of 6%. Let's repeat the entire equation now in the second example in this section, which is example number 6. Determine the percentage error if the radius of the Earth is measured to be 3,950 miles with an error of, oh goodness, that should be just plus or minus 100 miles. Okay, let's remind ourselves how we got started. Remember that this plus or minus 100 miles represents the error in the radius, which can also be written as dr. So our dr has to be less than or equal to a positive 100 miles and greater than or equal to a negative 100 miles. Now what do we need to do? Let's remember from previous work what we did next. Scrolling up, the next thing that we did was we took the volume of the sphere, 4/3 pi r cubed, and we did implicit differentiation on both sides to come up with the formula that dV is equal to 4 pi r squared dr. Now that we have dV, we know that we can place dV between these two expressions here with 4 pi r squared. So we have dV less than or equal to 4 pi r squared times the 100 miles on the upper end and greater than or equal to the 4 pi r squared with the negative 100 miles on the lower end. Now what do we need to do next? The next step is to approximate the value of the volume so that we can find the relative error. We're going to use the formula 4/3 pi r cubed, but we're going to use the measured value of the radius for our volume since we don't know exactly what the error is. That gives us a radius of 3,950, which gives us 4/3 pi times 3,950 quantity cubed. And this will give us cubic miles when we're done. Then we take this equation here and we divide by that expression in all three parts. We could take this negative here and pull it to the front so that it's sitting on the far left instead of in the middle. Then we have each part divided by the volume expression that we got previously, which is going to be the 4/3 pi r squared. Oops, my bad. I forgot to put in r, which is 3,950 miles cubed. This is the volume for all three parts. This is the same r that we have here, where r represents 3,950. If we do some reduction, notice that we do get quite a bit of reduction on both sides. Let's work out what the numbers turn out to be. This time we'll do the arithmetic together. Notice that we have a 4 canceling a 4 and a pi canceling a pi, and we have 2 of the radius in the numerator and 3 in the denominator, which leaves us 3,950 in the denominator here. This 3 will flip to the top since the denominator of the denominator is the numerator, or the bottom of the bottom is the top. This will give us a negative 3 times 100 with the miles on both, and they'll cancel. Since our units cancel, it results in just a number, which gives us the error. This is going to be divided by 3,950 miles, so the miles cancels the miles. On the right side, we have dV divided by V, which is less than or equal to, again, cancellation of the 4, cancellation of the pi, cancellation of 2 of the 3,950s. The 3 flips to the top. We have 100 times miles, and in the denominator, 3,950 miles. Now let's take and see what this value turns out to be. Basically, we've got negative 300 over 3,950 on the far left. And that gives us, if I can see correctly, a negative 0.07595 less than equal to dv over v, which is less than equal to the positive of the same value. That means that my relative error here is going to be the value of 0.07, well, let's call it 6. The relative error or percentage error is converting it into a percent, and the percentage error is about 7.6%, which means that we're probably off by as much as 7.6%. This is how you would compute the percent error. Now, a word about how important this last little section is. Calculating the amount of error is not something that is vastly important in what we're doing right now, but when you become an engineer, this will be hugely important. So for the Calculus 1 course, it may be a 1 out of 10, but in your future career, I bet you this is a 10 out of 10. So it is something that you'll want to pay some attention to and make sure you understand. The thing I'm most likely to test you on, however, are the first 3 examples where we use the tangent line linear approximation to approximate things like square roots and cube roots. This is the end of the video, and I hope it helps you with your homework.